Right now, you are certain of a few things. The floor beneath you is solid. The room around you is real. Your past is settled, and the world keeps existing, even when you close your eyes. These feel like the most basic facts of being alive. Physics has spent the last 100 years dismantling all of them, with experiment. Tested, repeated, Nobel Prize-winning experiment. What the data shows is that reality does not behave the way any of us assumed. Particles exist in multiple states at once. Distant objects connect instantaneously. Observing something changes what it is. And the greatest physicists alive cannot agree on what any of it means. Subscribe if you enjoy this, because the ground is about to disappear. Consider what you are certain of right now. The floor beneath you is solid. The walls of the room you occupy are fixed in place. The objects around you have definite shapes, definite positions, definite physical presence. You can press your hand against a surface and feel resistance. You can set something down and expect it to remain where you put it. When you leave the room continues to exist. When you close your eyes, the world goes on. These are not beliefs you hold carefully or tentatively. They are so obvious they have never required examination. They are the foundation beneath all other foundations. What physics has found, through a century of increasingly precise experiment, is that this foundation is not what it appears to be. The universe, at the level where its actual rules operate, does not behave the way any of our intuitions suggest. The solidity of the floor, the fixed position of the walls, the definite presence of every object around you, all of these are features of a large-scale approximation that holds well enough for the lives of creatures like us. But at the level where atoms interact and particles are born and measured, none of it is like this. Properties do not exist before they are measured. Distant particles are connected in ways that no signal can explain. The very concept of an independent reality, one that exists the same way whether or not anyone is looking, has been shown, by the most precise experiments in science, to be something the universe does not provide. The Nobel Prize in Physics in 2022 was awarded for proving this in the laboratory. The prize citation stated plainly that the experiments demonstrated the world violates local realism. Local realism is the technical name for the assumption that objects have definite properties before and independent of measurement, and that events here cannot instantaneously affect things over there. Both assumptions turned out to be wrong. Not probably wrong, or wrong in some exotic fringe case. Wrong. Demonstrated in experiment after experiment over 50 years, confirmed with increasing precision, awarded with the highest honor in science. This is the starting point. Not a hypothesis or a speculation, but a proven result that most people have never heard stated clearly. The universe is not locally real. Something more fundamental and more unsettling has taken its place. And exactly what that something is, what the universe is actually doing at its foundation, is the question that has been driving physics forward and driving physicists to the edge of comprehension for 100 years. Let us begin with the experiment that started all the trouble. For most of the history of science, the question of whether light was made of waves or particles seemed like a technical debate that experiment could settle once and for all. Isaac Newton thought particles traveled in straight lines, explained why light cast sharp shadows, and matched what you would expect if light were made of small, fast-moving objects. Christian Huygens disagreed. He proposed that light was a wave, like sound, propagating through a medium and capable of bending and interfering. In 1801, Thomas Young settled the question, or so it seemed. He cut two narrow slits into a barrier and passed light through them onto a screen. If light were particles, you would expect two bright bands on the screen, one behind each slit, where the particle streams would pile up. Instead, Young observed an interference pattern, alternating bands of bright and dark. In the bright bands, more light arrived than from either slit alone. In the dark bands, no light arrived at all, even though both slits were open. This could only happen if light waves passing through the two slits were superimposing, adding together where their peaks aligned, cancelling where a crest met a trough. The pattern was unmistakable. Light was a wave. Young's experiment stood as the decisive answer for a century. Then Albert Einstein published a paper in 1905 explaining the photoelectric effect, the ejection of electrons from a metal surface when light shines on it. The behavior of the ejected electrons depended on the frequency of the light, not its intensity. Brighter light produced more electrons but not more energetic ones. Higher frequency light produced more energetic electrons, even at low intensity. A smooth wave of light should deposit energy continuously. The electrons should gain energy proportional to the wave's intensity. The actual behavior required that light arrive in discrete packets, each carrying energy proportional to its frequency. These packets, which Einstein called quanta and we now call photons, were indivisible. An electron either absorbed one whole photon or absorbed nothing. The photoelectric effect could only be explained if light was quantized. Einstein received the Nobel Prize for this discovery. So light was particles? The interference pattern demanded waves. The photoelectric effect demanded particles. Quantum mechanics, developed over the 1920s, resolved the tension not by choosing one, but by revealing that the choice was wrong. Light is neither a wave nor a particle in the classical sense. It is something that behaves as a wave in some experimental situations and as a particle in others. And the behavior it exhibits depends not on any intrinsic property of the photon, but on what the experiment is designed to measure. The experiment that makes this starkest is the double-slit experiment performed with single photons. Fire photons, one at a time, through a double-slit barrier. Each photon arrives at the screen as a single dot, one mark in one place, exactly as a particle would. But fire thousands of photons this way, keeping careful track of where each dot falls, and the accumulated pattern is an interference pattern. The dots do not pile up in two bands behind the two slits. They assemble into the same alternating stripes of concentration and absence that Young observed with continuous light. Think about what this means. Each photon, sent alone, arrives as a single particle, but where it arrives depends on a probability distribution that has the shape of a wave interference pattern. The only way this can happen is if each photon, in transit, travels as a wave. Each photon passes through both slits simultaneously, interferes with itself, and lands at a location determined by the resulting wave pattern. The single particle, alone, indivisible, arriving at one point, somehow navigated both slits at once. Now add detectors at the slits to find out which slit each photon passes through. The interference pattern vanishes immediately. Every photon now passes through one slit or the other, and the dots pile up in two bands. The classical particle pattern. Remove the detectors. The quantum interference returns. The presence of any device that could reveal which path the photon took, whether or not the information is ever actually read by a human being, destroys the superposition. The physical availability of the path information is what matters, not the knowledge or curiosity of any observer. This experiment has been performed with electrons, with atoms, with increasingly complex molecules. A 2019 experiment demonstrated quantum interference with molecules containing more than 2,000 atoms, objects large enough to be resolved by electron microscopy. There is no natural size at which quantum behavior stops. The boundary between quantum and classical is not found in nature. It emerges from practical limitations in isolating systems from their environments. And the quantum behavior beneath everything keeps revealing itself whenever those limitations are carefully controlled. The concept this experiment demonstrates is superposition. Before measurement, a quantum system does not occupy a single definite state. It exists in a superposition of multiple possibilities simultaneously. Each possibility has a probability amplitude, a complex number whose square gives the probability of that outcome if measured. The amplitudes are real physical quantities. They interfere. Their interference produces the wave patterns we observe. And the critical, counterintuitive point: the superposition is not a description of our ignorance about which state the system secretly occupies. It is a description of the actual physical state of the system. The system genuinely is in multiple states at once. This claim that quantum indeterminacy is a feature of the world rather than a feature of our knowledge was controversial for decades. The instinctive response, then as now, is that particles must secretly be in one definite state even when we do not know which state that is. The randomness of quantum mechanics, on this view, reflects our ignorance of hidden information, hidden variables, properties of the particles that are real but inaccessible to current measurements. This was Albert Einstein's position. It was reasonable, clearly articulated, and it led to a prediction that experiment has conclusively shown is wrong. But before we get to that proof, there is a deeper problem to sit with. The governing equation of quantum mechanics, the equation that describes how quantum states evolve, is completely silent about what happens during measurement. The Schrödinger equation, written by Erwin Schrödinger in 1926, describes the evolution of quantum wave functions over time. It is deterministic. Given the wave function at one moment, the equation precisely specifies the wave function at every future moment. It is linear. Superpositions simply continue evolving as superpositions. A particle in superposition, governed by the Schrödinger equation, remains in superposition. The equation has no mechanism for resolving the superposition into a single, definite outcome. But in every laboratory, every measurement produces a single, definite outcome. The detector either clicks or it does not. The meter reads one specific number. The scientist records one specific result. Somewhere between the quantum system and the classical measurement record, the superposition resolves. The quantum possibilities reduce to one classical actuality. The Schrödinger equation does not contain the rule that governs this transition. So the standard formulation of quantum mechanics contains two separate rules that coexist uneasily. The first: quantum systems evolve according to the Schrödinger equation continuously and deterministically. The second: when measured, the wave function collapses to one of the possible outcomes, with probability given by the square of the amplitude. The collapse rule is not derived from the Schrödinger equation. It is inserted as an additional postulate because without it, the theory cannot match what is observed in the laboratory. This is the measurement problem. The theory that has been more precisely confirmed than any other equation in science contains a fundamental gap at its most important juncture. It tells us what we will find when we measure. It does not tell us what happens when the measuring takes place. And it does not tell us what the system was doing before the measurement occurred. Erwin Schrödinger, who wrote the equation, understood the weight of this problem deeply. In 1935, he published a paper that introduced a thought experiment designed to make the measurement problem inescapable at the scale of everyday life. A cat is placed inside a sealed box. Inside the box, a radioactive atom is connected through a detector and a trigger mechanism to a sealed vial of lethal gas. The atom is quantum. Before measurement, it exists in a superposition of decayed and not decayed, each with some probability. The mechanism is calibrated so that if the atom decays, the vial is broken and the cat dies. If the atom does not decay, the cat lives. Apply the Schrödinger equation honestly. The atom's superposition entangles with the detector. The detector's superposition entangles with the trigger. The trigger's superposition entangles with the vial. The vial's superposition entangles with the cat's biological state. The cat ends up, according to the Schrödinger equation, in a superposition of alive and dead. Both branches coexist in the quantum state of the closed box until someone opens the box and looks. Schrödinger intended this as a demonstration of the obvious. Applying quantum mechanics literally to a macroscopic system produced nonsense. Cats are not alive and dead simultaneously, and any theory that says they are must be wrong somewhere, He expected the physics community to identify the error and fix it. Instead, 90 years later, the error has not been identified. The Schrödinger equation has no built-in scale at which it ceases to apply. Every attempt to specify, from first principles, where quantum behavior ends and classical behavior begins, has produced either circular arguments or arbitrary assumptions. Experiments have pushed quantum superpositions into larger and larger systems, with no natural stopping point appearing. The cat thought experiment was supposed to be a quick proof that the theory was incomplete. It became instead a permanent map of the deepest problem in physics. The most widely taught response to the measurement problem is the Copenhagen interpretation, assembled primarily by Niels Bohr and Werner Heisenberg in the late 1920s. Its core claim is deliberate minimalism. Quantum mechanics is not a description of what exists, but a tool for predicting what will be observed. The wave function is a mathematical device, not a physical object. Properties do not exist before measurement. They are created by measurement. Asking what the cat is doing before you open the box is not a question physics needs to answer. Bohr argued this with philosophical sophistication. He drew on traditions in philosophy of science that questioned whether physical theories were required to describe a mind-independent reality or only to predict observations. For Bohr, the demand for a description of unobserved reality was a remnant of classical intuitions that quantum mechanics had superseded. Accept that physics describes what observers find, and the measurement problem dissolves. There is nothing to explain because there is no fact about the state of the system before measurement. The Copenhagen interpretation has been extraordinarily productive as a working framework. Most practicing physicists use it implicitly every day. The calculations work perfectly. The predictions match every experiment. There is no laboratory test that Copenhagen fails, and the interpretation is not obviously wrong in any logical sense. But it comes with a price. By refusing to describe what happens between measurements, Copenhagen places measurement itself, undefined, unexamined, attributed to a macroscopic classical apparatus that is itself made of quantum particles, at the foundation of everything. The definite classical world depends on measurement, and measurement is never explained. The theory that describes all of nature rests on a foundation that it refuses to examine. Albert Einstein refused this bargain. He believed the world had definite properties, whether or not anyone was looking. He believed quantum randomness was a sign of incomplete theory, not a fundamental feature of nature. Somewhere beneath the wave function were hidden variables, real physical properties determining outcomes in advance, which quantum mechanics did not describe because it lacked access to them. The indeterminacy was epistemic, not ontological, a limitation of our knowledge, not a feature of the universe. In 1935, Einstein worked with Boris Podolsky and Nathan Rosen to construct a thought experiment that would, he hoped, make the incompleteness apparent. Their paper, known by their initials as the EPR argument, described two particles that had interacted and then separated. Measuring one would instantly reveal correlated information about the other. In the hidden variable picture, the particles had those properties all along. Measurement revealed a pre-existing answer. In quantum mechanics, the measurement appeared to instantaneously determine the state of the distant particle. Einstein called this spooky action at a distance and found it incompatible with the relativity principle, that no influence could propagate faster than light. Niels Bohr responded that Einstein's analysis rested on classical intuitions that quantum mechanics had shown to be invalid. The debate became one of the most famous in 20th century science and remained genuinely unresolved for 30 years. Not because neither side could argue well, but because neither side could point to an experiment that would settle the question. The dispute seemed permanently philosophical. Then, in 1964, John Bell published a paper that changed everything. Bell was an Irish physicist who had been working at CERN. He had been thinking carefully about the EPR argument and found a mathematical crack in its foundation. The crucial insight: if particles carried hidden variables that predetermined measurement outcomes, and if those hidden variables were local, meaning each particle carried its own information without instantaneous reference to the other particle, then the correlations between measurements of the two particles would be bounded by a specific mathematical inequality. Bell's inequality specified the maximum correlation that any local hidden variable theory could produce. Quantum mechanics predicted correlations that could exceed Bell's inequality for certain measurements on certain entangled states. If the predictions of quantum mechanics were correct, Einstein's hidden variable picture was wrong. Not less convincing, not incomplete. Wrong. This was not a philosophical argument. It was a mathematical theorem that made a testable quantitative prediction. The two worldviews could be distinguished by measuring actual correlations in an actual laboratory. The experiments began. Stuart Friedman and John Clauser built the first apparatus to test Bell's inequality directly in 1972 using entangled photons. The correlations they measured violated Bell's inequality, exactly as quantum mechanics predicted. Some physicists suspected loopholes in the experiment. Clauser and others worked to close them. Alain Aspect and his group in Paris performed 3 progressively more rigorous experiments in 1981 and 1982, closing the most important loophole: the possibility that the experimental settings chosen by the experimenters could have been signaled in advance to the particles. Aspect's results confirmed violation of Bell's inequality with high precision. The experiments continued for decades. Each new generation of tests was more precise, used different particle types, closed additional loopholes. The violation was confirmed every time, under every condition, in laboratories on multiple continents. The debate shifted not about whether the violation was real, but about which remaining loopholes might conceivably explain it. In 2015, a team at Delft University of Technology in the Netherlands closed all remaining loopholes simultaneously. They used entangled electrons rather than photons, taking advantage of the ability to measure electrons without the efficiency problems that plagued early photon experiments. The 2 electron measurement stations were separated by about a mile. The measurement settings were chosen after the particles had been emitted, ensuring no light speed signal from one station could reach the other before the measurement was made, and the measurements were performed within a time window short enough that no influence could travel between stations, even at the speed of light. Bell's inequality was violated. The result was clear. Local hidden variables were ruled out. The Nobel Prize, awarded in 2022, confirmed the scientific consensus. The experiments of Aspect, Clauser, Zeilinger, and their collaborators had demonstrated that the world violates local realism. This means the universe cannot simultaneously be both local and real in the classical sense. Either events here can instantaneously affect things over there, which means non-locality is a feature of the universe, or particles do not have definite properties before measurement, which means physical reality, in the classical sense, does not exist between observations, or both. Both options represent a fundamental break from the intuitive picture of the universe. Both are accepted by serious physicists, and both raise the same underlying question, the one that Bell's theorem and its experimental confirmation make unavoidable. If the universe is not locally real, what is it? If particles do not have definite properties between measurements, what exists between measurements? If the definite world is created by observation, what is doing the observing? And what exactly is the act of measurement? These questions have been driving physics and frightening physicists for the better part of a century. The answers that have been proposed are among the strangest ideas in the history of human thought. They are all, in different ways, consistent with the experimental data, and not one of them gives back the solid, observer-independent, locally causal universe we thought we were living in. Quantum entanglement, the phenomenon at the center of Bell's theorem, deserves a closer look, because it is stranger than even the Bell experiments fully suggest. When two particles interact and become entangled, they share a quantum state. This is not a metaphor for being closely related or having a shared history. It means that the combined state of the two particles cannot be factored into separate states for each particle. There is no description of particle 1 and a separate description of particle 2. There is only a description of both together. This joint description persists across any distance. Once entangled, the two particles remain connected, no matter how far apart they travel. Measure the spin of one particle along a chosen axis, and you get one of two results. Call them up and down. Immediately, if you then measure the spin of the other particle along the same axis, you get the opposite result. If the first was up, the second is down. Every time, without fail, regardless of the distance between them. Before either measurement, neither particle has a definite spin. The entangled state is a superposition. One branch where the first is up and the second is down, another branch where the first is down and the second is up. The particles have no individual spins. The spin is a property of the joint system, not of the individual particles. When you measure one, you are not revealing which spin it secretly had. You are forcing the joint system into one of the two possible definite configurations. And in that instant, the configuration of the distant partner is established as well. The measurement results are not just correlated, they are correlated more strongly than any pre-existing agreement between the particles could produce. Bell's theorem is precisely the proof of this. If the particles had pre-existing spins, set when they were created and carried through space as real, definite properties, the correlations between measurements made along different axes would satisfy Bell's inequality. They do not. The correlations are stronger. Only quantum mechanics, with its insistence that the spins were genuinely undefined until measurement, can explain the actual data. What kind of universe has this property? A universe where things that are separated in space are not fully independent. A universe where the information needed to describe a system is distributed non-locally, where separating two parts of a system in space does not separate their physical descriptions. This is not a limitation of our current knowledge. It is a structural feature of reality that Bell's theorem and 50 years of experiments have confirmed. Some physicists argue that the non-locality of entanglement is a sign that the universe is fundamentally holistic, that the attempt to decompose it into independent local parts is a useful fiction that breaks down at the quantum level. Others argue that the non-locality is physically real, but carefully constrained, unable to propagate classical information, and therefore compatible with special relativity in practice, even if uncomfortable with it in spirit. Still others argue that accepting non-locality is simply the price of accepting quantum mechanics as a complete description of reality, and that the price is worth paying. What no serious physicist argues is that the entanglement is not real. The correlations have been measured. The violation of Bell's inequality has been confirmed. The entanglement is there. The universe has a non-local structure that nothing in our everyday experience prepares us for, and every attempt to explain it away has been ruled out by experiment. The practical implications of entanglement have driven enormous investment in quantum technology. Quantum computers that use entanglement to perform certain computations exponentially faster than classical machines. Quantum cryptography that uses entanglement to make eavesdropping physically detectable. Quantum sensors that achieve precision beyond classical limits. These applications are real, they work, and they depend on quantum entanglement being exactly as strange as quantum mechanics says it is. Every quantum computer that runs a calculation is, in a sense, a daily experiment confirming that the universe is not locally real. But the technological applications, impressive as they are, do not touch the deepest questions. What is a quantum state, really? What is the world doing between measurements? When two entangled particles correlate instantly across vast distances, what is the mechanism? How does measuring one particle know about the configuration of the other in time for the correlation to work? The Copenhagen interpretation's answer: do not ask. The correlation is observed. The probability is correct. Nothing more needs to be said. Many physicists have found this answer increasingly unsatisfying as quantum mechanics has been applied to more and more complex systems, as the measurements have become more and more precise, and as the scale of what can be placed in quantum superposition has expanded decade by decade. The questions about what is happening have not gone away. They have become more pressing, and the alternative interpretations of quantum mechanics that have been proposed, each attempting to answer the questions that Copenhagen refuses, are each strange in their own way, each demanding that we give up something we thought was obviously true. The landscape of quantum interpretations is not a collection of equivalent options between which personal preference alone decides. Each interpretation accepts certain features of reality and rejects others. Each is internally consistent. Each predicts exactly the same results as every other interpretation for every experiment that has been performed so far, and each provides a radically different answer to the question, what is actually going on? What comes next is an exploration of those answers, an honest examination of what physicists who have thought most carefully about these questions have concluded or failed to conclude after a century of effort. The answers are not reassuring, but they are the answers that the evidence supports, in different ways, with different costs. And confronting them is unavoidable if you want to know what physics has actually found about the nature of reality. The floor is solid, the walls are fixed, the room exists when you leave. All of this is true as a description of the world at the scale of human experience, where the effects of quantum mechanics are washed out by decoherence and the sheer number of particles involved. But it is not the whole truth. It is a functional approximation, and the actual thing that is being approximated is something far stranger, far less settled, and far less comfortable than the comfortable certainty of everyday experience suggests. The next part of the story involves the physicists who refused to stop asking and the ideas they arrived at, ideas that are, depending on your temperament, either the most fascinating discoveries in the history of human thought or the most frightening, usually both. The world we move through every day is not quantum, it is classical. Objects stay where you put them. Properties are definite. Outcomes are certain to a degree that makes life predictable and navigation possible. This classical reliability is real. It is not an illusion, but it is not the ground floor of reality. It is the penthouse, built on top of something far less familiar. Understanding why the classical world looks the way it does, given that the underlying physics is quantum, requires a concept called decoherence. And understanding decoherence is essential to understanding why the measurement problem is harder to solve than it first appears. Every quantum system in the real world is in contact with an environment. An electron in a laboratory is surrounded by photons, by other electrons, by the thermal radiation from the walls. An atom in air is constantly colliding with other atoms. A molecule in a cell is embedded in a thermal bath of surrounding molecules. These environmental interactions do not leave the quantum system alone. They entangle it. When a quantum system in superposition interacts with even one environmental particle, the two become entangled. The superposition of the original system is now part of a larger superposition that includes the environment. When the environment involves two particles, the entanglement spreads to 3. When the environment involves 1,000,000 particles, which it does, in virtually any realistic setting, within a tiny fraction of a second, the superposition is shared across a 1,000,000 particle system. The effect on the original system is devastating for quantum behavior. The coherence, the phase relationship between different branches of the superposition that makes interference possible, gets distributed across the enormous environment. From the perspective of the original system, looking at it without tracking the environment, the coherence appears to have vanished. the interference patterns disappear. The system looks classical, like a mixture of definite possibilities with definite probabilities, rather than a superposition of coexisting states with interfering amplitudes. This process is decoherence. It happens fast. For a large object, a dust particle, a molecule visible to the eye, decoherence takes place in a time so short it cannot be meaningfully compared to any human-scale interval. The object's quantum nature is beaten out of it by its environment before any measurement instrument, no matter how fast, could ever hope to detect it. This is why you do not see your coffee cup in a superposition of locations. The quantum state of the coffee cup has decohered with the environment so thoroughly that the coherence between different spatial locations has been diluted below any possible detection threshold. Decoherence explains why the classical world looks classical. It explains why large objects do not maintain quantum superpositions. It explains why measurement devices produce definite readings rather than superpositions of readings. When a detector registers the position of a particle, the detector's quantum state entangles with the particle's state. The combined system decoheres with the environment almost instantly, leaving the detector in what looks like a definite state correlated with one of the particle's possible positions. But here is the critical limitation of decoherence as a solution to the measurement problem. Decoherence explains why different possible outcomes stop interfering with each other. It does not explain why one specific outcome is the one that actually happens. After decoherence, the system is described by a mixture of possible outcomes, each with a probability. But in the real world, one outcome occurs. The cat is alive, or the cat is dead. The decoherence has separated the two branches and made them unable to interfere, but both branches are still there in the mathematics. The Schrödinger equation, run through decoherence, produces a state in which the alive branch and the dead branch coexist, each with its proper probability, unable to interfere with each other. From the inside of one branch, you see only one outcome, and decoherence tells you why you do not see any interference between the branches. But it does not pick a branch. It does not explain why this particular outcome happened rather than the other. The measurement problem, at its deepest level, remains untouched. This is the central divide in the interpretation of quantum mechanics. On one side are the interpretations that accept that the wave function, including all its branches, is the complete description of reality and conclude that all branches genuinely exist, that the apparent uniqueness of outcomes is an illusion produced by our position inside one branch. On the other side are the interpretations that insist on a unique, definite outcome and introduce additional physics, additional rules, or additional metaphysics to explain how the universe picks one result from all the quantum possibilities. Neither side has found a definitive answer. Neither side has found a decisive experimental test. The debate has been running for a century and shows no signs of reaching a resolution through pure argument. The question of what quantum mechanics means has become, for some physicists, the most important unanswered question in science. For others, it remains a philosophical distraction from the practical work of applying quantum mechanics to calculate real results. Both attitudes are defensible, but the question does not go away just because you choose to ignore it. The universe is doing something. At every quantum event, every decay, every absorption, every scattering, the superposition is evolving, the entanglement is growing, and somewhere in the physics, the definite outcomes that fill the laboratory records are being produced. Whether that somewhere is a physical collapse, a branching of reality, or an act of an observer acquiring information about the world remains, after a century, genuinely open. The urgency of this question is not merely philosophical. Quantum computers are being built that must maintain quantum coherence across thousands of qubits, exploiting superposition and entanglement for computational advantage. Understanding decoherence, how it happens, how fast, how it can be prevented, is an engineering imperative. The technology of the 21st century is being built on foundations that are not fully understood, and beyond technology, there is the simpler, deeper question: what is the universe? Not what does it do, but what is it? What is a quantum state? What exists between measurements? What is the nature of the reality that physics has been describing with such extraordinary precision for 100 years, while remaining unable to say what it actually is? The history of attempts to answer this question is a history of courage and ingenuity and failure, not because the attempts were foolish, but because the question turned out to be harder than anyone supposed, and harder, perhaps, than any of us is naturally equipped to grasp. The human mind evolved to navigate a world where large objects have definite positions, where causes precede effects, and where the past is fixed and the future is open. The quantum world inverts or suspends all of these assumptions. Intuition is not just unhelpful, it is actively misleading. Every time someone has trusted their intuition about what quantum mechanics must mean, the experiments have told them they were wrong. What remains is the experiment, the data, the correlations, the interference patterns, the violated inequalities, the laboratory records that accumulate outcome by definite outcome, while the theory underlying them maintains an irreducible ambiguity about what any of it means. The evidence is clear, the interpretation is not, and that combination, clear evidence, unclear meaning, is the most unsettling position any science has ever occupied. What Bell's theorem and its experimental confirmation actually prove deserves to be stated with more precision than it usually receives, because the implications are often softened until they no longer mean what the evidence shows. The theorem is a mathematical result about correlations. It says, if quantum particles carry definite, pre-existing properties, hidden variables, and if those properties are local, meaning each particle's properties are its own and are not instantly affected by events happening elsewhere, then the correlations between measurements of entangled particles will satisfy a specific mathematical bound. This bound is Bell's inequality. The experiments violated this bound, not by a small margin, not within experimental uncertainty, not in a way that could be attributed to measurement imprecision or sampling bias. The correlations exceeded Bell's inequality by a substantial factor, exactly as quantum mechanics predicted, and the 2022 Nobel Prize was awarded to the physicists who demonstrated this most precisely and compellingly. Their citation stated explicitly that the experiments revealed the world violates local realism. Two conclusions follow. Either the world is non-local, events here can instantaneously affect things over there, through connections that cannot transmit information, but that are physically real, or the world is not real in the classical sense. Particles do not have definite properties between measurements, and the act of measurement creates the property rather than revealing one that was already there. Most contemporary interpretations of quantum mechanics accept some version of the second option, because non-locality sits uncomfortably with special relativity. But neither conclusion is comfortable, and neither gives back the straightforward, observer-independent universe that common sense assumes. The first conclusion, non-locality, is accepted by physicists who work with pilot wave theory, also called Bohmian mechanics. In this picture, particles always have definite positions, but they are guided by a pilot wave that responds instantly to any change anywhere in the universe. The wave is global and non-local. This makes the theory non-local in the most explicit possible way. Every event in the universe is, in principle, immediately reflected in the pilot wave, which immediately affects the guidance of every other particle. The correlations of entanglement are not mysterious in this picture. They are the natural result of particles being guided by the same global wave, which updates instantly when a measurement is made. The second conclusion, that definite properties do not exist before measurement, is the more widely accepted option, though it comes in many different versions that disagree profoundly on what it implies. The debate between those versions is where the deepest questions live. Quantum entanglement, understood properly, reveals something about the structure of the universe that goes beyond any particular interpretation. When two particles are entangled, there is no complete description of particle 1 that can be specified independently of particle 2. This is not a limitation of our knowledge. It is a fact about the mathematical structure of the quantum state. Entangled particles are described by a joint wave function that cannot be factored into separate wave functions for each particle. The entanglement is a real structural feature of the state. This means that separating entangled particles in space does not separate their descriptions. You can move the particles to opposite sides of a galaxy. Their joint quantum state remains a single, unified mathematical object. Measuring one particle, anywhere, changes the complete description of the pair, not by sending a signal across space, but because the pair's description was always a single thing. The measurement does not transmit information. It selects one branch of the joint state, and the other particle finds itself in the corresponding branch of that selection, wherever it is. The non-local correlations of entanglement cannot be used to send messages. If you and a partner each have one particle of an entangled pair, you cannot use the correlations to communicate. Your outcomes are individually random. You have no control over which result you get. The coordination only becomes apparent when you compare notes through a classical channel, but the coordination itself is real and instantaneous. The universe has a structure that connects distant parts in ways that classical physics could never accommodate. What this structure means for the nature of space and connection is one of the deepest open questions in physics. Some physicists believe entanglement is the fundamental fabric from which the structure of space itself is woven, that spatial distance is not primary but emergent, and that the entanglement structure of quantum systems is the more fundamental underlying geometry. This is speculative, but it is not frivolous speculation. It is being actively investigated in research programs connecting quantum information theory to quantum gravity. For our purposes, the key point is simpler. The universe is not made of independent, locally defined parts. The parts are connected in ways that make local independence an approximation rather than a deep truth. And this means that the classical picture of reality as a collection of separate objects, each with its own properties, each interacting only through local forces, is not accurate at the level where the universe's actual rules apply. The decoherence theory, developed in the 1970s and 1980s primarily by Dieter Z and Wojciech Zurek, was the most important conceptual advance in the foundations of quantum mechanics since the original Copenhagen debates. Before decoherence was understood, the gap between the quantum world and the classical world seemed to require an unexplained physical mechanism, some process that selected one outcome from the quantum possibilities. Decoherence provided a more careful answer, though not the complete answer it is sometimes advertised to be. Here is the mechanism. Every quantum system in the real world is in contact with an environment. The environment is made of other quantum particles, photons, air molecules, thermal radiation. Every interaction between the quantum system and the environment creates entanglement between them. Once entangled, the environment carries information about the quantum system. The phase relationships between different components of the superposition, the delicate quantum coherence that makes interference possible, become distributed across the enormous number of environmental particles. From the perspective of the quantum system alone, looking at it without tracking the environment, the coherence disappears. The system that was in a quantum superposition of two states now looks like a classical mixture. State A with probability p, state B with probability 1 minus p. The interference terms, the terms that made the quantum superposition different from a classical mixture, have been diluted into the environment beyond recovery. For a large object like a cat, a dust particle, or any macroscopic system, decoherence happens in a time too short to express in ordinary language. Environmental particles are constantly interacting, constantly entangling, constantly extracting and distributing information about the quantum state. The quantum coherence of large systems is effectively zero by the time any measurement could detect it. This explains why you do not see everyday objects in quantum superpositions. The table in front of you is in constant contact with photons, air molecules, and thermal radiation. Any superposition of the table's position is decohered essentially instantaneously. The table behaves classically because its quantum coherence is destroyed too fast to manifest as any observable quantum behavior. But decoherence has a limit. It explains why different branches of the quantum superposition stop interfering with each other. It does not explain why one branch is chosen. After decoherence, you have a system that looks like a classical probability distribution. A live cat with probability 1/2. Dead cat with probability 1/2. But in the real world, when you open the box, you find one definite outcome. The cat is alive, or the cat is dead, not a mixture. One result. Decoherence took the question, why does measurement produce definite outcomes instead of quantum superpositions? And transformed it into the question, why does measurement produce one specific outcome rather than a classical mixture? The gap is smaller, but it is still a gap. The measurement problem was not solved by decoherence. It was refined. And the refined version is, if anything, harder to answer. This is where the many worlds interpretation enters, and why it has been gaining ground among physicists who think carefully about foundations. The proposal was made in 1957 by Hugh Everett III, a Princeton doctoral student working under John Archibald Wheeler. Everett's insight was radical in its simplicity. What if the wave function never collapses? What if the Schrödinger equation applies to everything, without exception, and measurement is not a special event that interrupts quantum evolution? If this is right, here is what happens during measurement. The particle in superposition entangles with the measuring device. The device enters a superposition of states, corresponding to the different possible results. The scientist reading the device becomes entangled with the device. The scientist enters a superposition, one branch where they recorded result A, another where they recorded result B. The laboratory enters a superposition, the building, the city, the world. Everything that interacts with the measurement chain becomes part of an expanding, entangled superposition. From inside one branch, this looks exactly like what we experience. One definite result, one pointer pointing to one position, one entry in one notebook. The scientist in the A branch is a fully coherent, self-consistent version of reality in which A happened. The scientist in the branch is equally coherent, equally real. Both exist. The wave function did not collapse. It branched. Every quantum event branches the universe. Not just dramatic events. Every photon absorbed by a molecule, every radioactive decay, every quantum scattering event splits the universe into branches where each outcome occurred. The number of branches grows without limit, at a rate that exceeds any ordinary description of large numbers. The many worlds interpretation requires no extra physics, no collapse mechanism, no special status for measurement. The Schrödinger equation runs everywhere, always, without exception. What you get is a universe that is vastly larger than it looks from inside any one branch. A universe that contains every possible version of every possible event, all equally real, all developing in parallel and unable to interact with each other after they diverge. Everett's interpretation was received with skepticism in 1957. His advisor Wheeler thought it was brilliant but unsaleable to the physics community. Everett made some concessions to convention, submitted the thesis, and left academia entirely. He spent his subsequent career in defense research and died in 1982, before his ideas had been fully rehabilitated. The rehabilitation came partly through Bryce DeWitt, who coined the term many worlds in the 1970s and championed the interpretation in publications aimed at broader readership. DeWitt's description, infinite parallel universes, constantly branching, was vivid and memorable, and helped the interpretation become widely known. Today, it is taken seriously by some of the most mathematically sophisticated physicists in the world. David Deutsch argues It is the only interpretation that takes quantum mechanics completely literally. David Wallace has developed the most rigorous formulation of it, addressing the hardest philosophical problems with formal precision. Sean Carroll writes and speaks about it with evident conviction. But there is a genuine, unresolved problem at the heart of many worlds, and it concerns probability. If every outcome of every quantum event occurs in some branch, what does it mean to assign probabilities to outcomes? The Born rule, the rule that says the probability of finding a result is the square of the magnitude of the corresponding amplitude in the wave function, works perfectly in practice. But in a many worlds framework, every result is certain to happen in some branch. The concept of probability seems to lose its meaning. Various responses have been proposed. Decision theoretic arguments attempt to show that a rational agent, knowing they are about to enter a branching event, should bet according to the Born rule probabilities, because that is the behavior that maximizes their expected self-interest across branches. These arguments are careful and sophisticated, and they are also controversial. Critics argue that they either assume what they are trying to prove or introduce assumptions that are not derivable from the Schrödinger equation alone. The probability problem in many worlds remains genuinely unresolved, and it is the main reason many physicists who find the interpretation appealing in other respects are not fully committed to it. A theory that cannot clearly explain what its probabilities mean is incomplete, however elegant it is in other respects. What many worlds does not require, and this is one of its most attractive features, is any special role for observers. In Copenhagen, measurement collapses the wave function, and measurement is performed by macroscopic classical devices, which are somehow not subject to the quantum rules that govern their constituent atoms. The boundary between quantum and classical, between the system and the apparatus, is never clearly specified. This is the hole at the center of Copenhagen. It relies on the very thing it refuses to examine. In many worlds, measurement is just entanglement. The measuring device, the scientist, the laboratory, all are quantum systems. All evolve according to the Schrödinger equation. All branch when quantum events occur. There is no classical quantum boundary, because everything is quantum. The classical world is not a separate domain. It is the stable, decoherent, nearly non-interacting structure that large-scale quantum systems settle into when they interact with large environments. This resolution of the classical quantum boundary is genuinely appealing. It is one of the main reasons many worlds has attracted serious defenders. But the cost of accepting it is accepting that you, right now, are not a single person. You are one branch of an endlessly branching quantum system. Every decision you have made, every coin that has been flipped near you, every radioactive decay that has occurred in your vicinity, all of these events have spawned new branches of the quantum state of the universe. In every one of those branches, a version of you exists, genuinely and physically, living out the consequences of the branched outcomes. Those versions are not imaginary. They are, in this interpretation, just as real as you are. You simply cannot communicate with them. This is not philosophy. This is the implication of taking the Schrödinger equation seriously, applying it to everything, and refusing to add any extra collapse postulate. It is the cleanest, most mathematically honest interpretation of the formalism, and it leads to a picture of reality so expanded, so strange, and so at odds with the intuitive sense of being a single person in a single world, that most people's first reaction is that it cannot be right. Whether that reaction is wisdom or instinct is what physicists are still arguing about. While the many worlds debate was developing, a completely different approach to the quantum measurement problem was gaining traction from a different direction. In 1996, Italian physicist Carlo Rovelli published a paper proposing what he called relational quantum mechanics. His starting point was not the collapse problem or the branching problem, but a more basic question. What does a quantum state actually describe? Rovelli's answer drew on an analogy with Einstein's theory of relativity. In special relativity, velocity is relative, an object does not have a single, absolute velocity. It has a velocity relative to one reference frame and a different velocity relative to another frame. Both values are equally real. There is no frame-independent velocity that is the true velocity of the object. Velocity is a relational property. It exists in the relationship between two systems, not as an intrinsic property of either one. Rovelli proposed that quantum states work the same way. A quantum system does not have a quantum state in the abstract. It has a state relative to a specific system that has interacted with it. Measure an electron's spin and find it pointing up. That is a fact about the relationship between you and the electron. Relative to some other observer who has not interacted with the electron, it may still be in superposition. Both descriptions are equally valid. Neither is more fundamental. When Alice measures an electron and finds a definite result, the wave function collapses relative to Alice. This is a real fact. Relative to Alice, the electron now has a definite spin. But relative to Bob, who has not interacted with the electron, nothing has happened. Bob's description of the electron is still a superposition. Both descriptions are correct. They do not contradict each other because they are describing the electron's relationship to different systems, not a single absolute state of the electron itself. This dissolves the measurement problem in a specific way. The collapse is not a mysterious physical event that selects one branch of reality. It is the acquisition of information by one system about another, the establishment of a new relational fact. There is no universal, observer-independent moment of collapse. There is only the local fact of one system interacting with another and establishing a correlation. Relational quantum mechanics does not require branches, hidden variables, or modified equations. It requires only accepting that quantum states are always relative to observers, fundamentally and irreducibly. There is no observer-independent quantum state of anything. This is a deep concession. It means that there is no complete description of the universe that is true from no particular perspective. Every description is made from somewhere, by some observer, and is relative to that observer's interactions with the world. The universe has no absolute state. It has only the web of relational states established by interactions between its parts. The implications for what we mean by reality are profound. Classical physics offered the vision of an objective reality, a world that exists in some definite state, independent of any observer, which science could progressively map and describe. Special relativity preserved this vision for most things, making only velocity and simultaneity observer-dependent. But relational quantum mechanics extends observer dependence to every physical property. The position of a particle, its spin, its energy, all are facts only relative to a specific interacting system. Rovelli has pressed this point with characteristic bluntness. In a 2025 article in Quantum magazine, he wrote, "The best way of conceptualizing reality in light of modern science is in terms of the relative information that pieces of nature have about one another. We can only say how the world looks from our limited, biased perspective. We have to live with this lack of total description over reality. This is not a mystical statement about the limitations of the human mind. It is a precise, technical claim about the mathematical structure of quantum mechanics. The formalism does not contain a perspective-independent description of reality, and this is not a limitation that better theory will overcome. It is a feature of the universe. Relational quantum mechanics has attracted serious interest, though also serious objections. Critics argue that it is not clear how intersubjective agreement works in this framework, why different observers, each with their own relational facts, all agree on the results of measurements they compare. Rovelli's answer involves the consistency of quantum mechanics. The framework guarantees that when two observers exchange information about measurements, their relational facts are consistent. But the details of how this consistency is enforced without an objective underlying reality remain disputed. a different response to the observer problem in quantum mechanics, developed contemporaneously with relational quantum mechanics, but coming from a very different philosophical tradition, is cubism, a name that stands for quantum Bayesianism. Cubism was developed primarily by Christopher Fuchs, Carlton Caves, and Rudiger Schack, starting in the late 1990s. Cubism's starting point is radical. The quantum state is not a feature of the world. It is a feature of an agent, a conscious, rational being capable of taking actions and experiencing consequences. The wave function that a physicist assigns to a quantum system represents not the system's properties, but the physicist's expectations about what they will experience when they interact with the system. When an experimentalist assigns a wave function to an electron, they are not describing the electron. They are describing their personal probability distribution over the possible outcomes of any measurement they might perform. The Born rule, the formula that converts wave function amplitudes into probabilities, is not a law of nature describing objective propensities. It is a normative rule, a constraint on what a rational agent should believe, given certain prior experiences. In cubism, the wave function collapses when a measurement is made, not because anything physical happens to the electron, but because the agent's experience updates their beliefs. The physicist fires the electron at a detector, the detector registers a result, and the physicist's expectations for future measurements of the same electron are updated. This is exactly the same as how a rational person updates any belief in light of new evidence. There is no physical collapse, no branch, no special status for measurement. There is only an agent acting on the world and updating their expectations based on what they experience. This makes cubism highly resistant to the measurement problem. There is no measurement problem in cubism because there is no objective quantum state to collapse. The problem dissolves, but at the cost of making quantum mechanics explicitly about agents and their experiences, rather than about an objective external reality. Critics of cubism raise several objections. The most common: if quantum states are just personal beliefs, why do all physicists agree on the statistics? When many experimentalists measure identically prepared electrons, they all get the same distribution of results. If their quantum states represent personal beliefs, what coordinates those beliefs? Cubism's answer: the world. Different agents, interacting with the same physical world, are constrained by the world to have consistent beliefs. The agreement reflects not a shared objective quantum state, but the fact that a single shared world imposes consistent experiences on all agents within it. This answer is philosophically defensible, but deeply unnatural for most scientists. Science is supposed to be about the world, not about what agents believe about the world. Cubism redraws the boundary between science and epistemology in a way that makes many physicists uncomfortable. Fuchs has been explicit about the philosophical implications. He draws on the American pragmatist tradition, William James, John Dewey, William Clifford, and argues that cubism represents a maturation of science's understanding of what it is actually doing. Science has always been done by agents with experiences. Taking that seriously means acknowledging that the output of science is always a description of what agents will find, not a God's eye description of the universe itself. Whether this is a deep insight or a philosophical retreat is contested, but cubism has attracted serious attention from physicists and philosophers of physics, and it resolves, or dissolves, a number of quantum puzzles that other interpretations struggle with. One of those puzzles is the Wigner's friend scenario, a thought experiment that has moved from philosophical puzzle to experimental test in the last decade and become one of the most unsettling results in modern physics. The scenario was proposed by Eugene Wigner in 1961. Wigner imagined a friend, let us call her Alice, sealed in a laboratory with a quantum particle. Alice performs a measurement on the particle, which is initially in a superposition. From Alice's perspective, the measurement collapses the wave function. She has a definite result. she knows which outcome occurred. Wigner, outside the laboratory, knows that a measurement was performed but does not know the result. He has had no interaction with the laboratory since the measurement. From Wigner's perspective, applying quantum mechanics honestly, the laboratory, including Alice and her measuring device, is in a superposition of two states. One, where Alice measured result A, and one where Alice measured result B. The two branches coexist in Wigner's quantum description of the laboratory. This produces a direct conflict. Alice says the wave function collapsed when she measured. Wigner says the laboratory is still in superposition. Both are applying quantum mechanics correctly from their respective perspectives. Both cannot simultaneously be giving a complete description of the same physical situation. Different interpretations resolve this differently. Copenhagen says, each observer should apply quantum mechanics from their own perspective without asking about the other perspective. The perspectives are incommensurable. Wigner's description is correct for Wigner. Alice's description is correct for Alice. There is no absolute fact about the quantum state. Many Worlds says, both perspectives are correct, and the apparent conflict is resolved by noting that Wigner is about to branch. When he opens the laboratory and interacts with Alice, his own quantum state entangles with hers, and he enters a branch where he and Alice agree on the result. Every branch has consistent internal fact. The apparent conflict was between different branches, not within a single branch. Relational quantum mechanics says, quantum states are always relative to observers. Alice's state description of the particle is relative to Alice's interaction. Wigner's state description of the laboratory is relative to Wigner's non-interaction. Both are correct relational facts. There is no absolute fact about the system. Cubism says, Alice's wave function is Alice's personal probability distribution, updated after her measurement. Wigner's wave function is his personal probability distribution, which has not been updated because he has not interacted with the laboratory. Both are correct representations of their respective epistemic positions. There is no objective quantum state to be in conflict. Every interpretation can handle the Wigner's friend scenario, but handling it requires each interpretation to give up something. Objective collapse, unique outcomes, observer-independent reality, or a single consistent set of facts. What changed the Wigner's friend scenario from a thought experiment to an experimental result was a paper published in 2019 by Massimiliano Proietti and colleagues at Heriot-Watt University in Edinburgh. The team used photons and optical components to simulate the Wigner's friend setup in a real laboratory. 4 simulated observers, 2 Wigners and 2 friends, each made measurements and predictions according to quantum mechanics. The results showed that the simulated observers could obtain facts that were mutually contradictory, facts that were each individually consistent with quantum mechanics, but could not both be simultaneously true within a single classical framework. The experiment was not straightforward to interpret, and physicists have debated its implications. But it demonstrated that the logical structure of the Wigner's friend paradox is not merely philosophical, it is physically realizable, and its implications are measurable. 2 observers, each applying quantum mechanics correctly, can genuinely disagree about facts in a way that quantum mechanics itself permits, and that no deeper fact can resolve. This is among the most disturbing results in modern physics. It does not mean that reality is subjective in a casual, personal sense. It means that quantum mechanics, applied universally to all observers, including conscious ones, implies a structure of facts that is irreducibly perspectival. There is no single, consistent, complete set of facts about a quantum event that applies equally to all observers. Each observer has their own quantum reality, and those realities can contradict each other without either being wrong. If quantum mechanics is correct and complete, and if observers are physical systems subject to quantum rules, this is not a paradox to be resolved. It is a feature of the universe to be accepted. A universe where different observers can have genuinely different, mutually contradictory facts about the same event is not the universe anyone expected to find. but it is the universe that quantum mechanics describes. The Wigner's friend experiment at Heriot-Watt was followed in 2018 by a theoretical result of even greater sharpness. Daniela Frauschiger and Renner published a thought experiment extending the Wigner's friend setup to multiple observers reasoning about each other's conclusions. Their theorem demonstrated something that the physics community found genuinely alarming: quantum mechanics, applied consistently to all observers, including those making measurements, leads to a logical contradiction unless at least one of three apparently reasonable assumptions is abandoned. The three assumptions are simple to state. First, there is only one consistent set of facts. Different observers cannot both be right if they give contradictory accounts of the same event. Second, an observer can use the results that another observer obtained from their measurements to make their own predictions. Third, quantum mechanics applies universally, including to observers themselves. These three assumptions look obviously true. The first says reality is not subjectively relative. Facts are facts, and contradictions cannot both be correct. The second says observers can reason from other observers' evidence, the basic operation of science, where experiments done in one laboratory constrain predictions in another. The third says quantum mechanics is a universal theory. It applies to atoms, molecules, measuring devices, and people with equal validity. The Frauschiger-Renner theorem shows that all three cannot simultaneously be true if quantum mechanics is correct. The proof is careful and has been checked many times. You must give up at least one. Each interpretation of quantum mechanics makes a different choice. Copenhagen gives up the third. It applies quantum mechanics to the measured system but not to the observer, treating the observer as a classical device that causes collapse rather than a quantum system subject to the Schrödinger equation. Many worlds gives up the first. There is no single consistent set of facts. Different branches have different facts, all equally real, none contradicting the others within their own branches. Relational quantum mechanics and cubism give up the first in different ways. Facts are relative to observers, and apparent contradictions between observers do not violate consistency because they are facts relative to different systems. Bohmian mechanics keeps all three but pays the price of radical non-locality built into its guide waves. No free lunch is available. Every interpretation of quantum mechanics requires abandoning something that seems self-evidently true. The debate between interpretations is the debate about which obvious thing is least costly to sacrifice. This may seem like a problem for experts to sort out while the rest of us live our lives. And for practical purposes, it is. No experiment yet devised can distinguish between the predictions of the different interpretations. They all produce the same numbers for every measurement. The interpretation you choose does not affect the outcome of any calculation. But the question is not merely academic. The different interpretations give different answers to the most basic questions you can ask about the universe. Does the world have a definite state when no one is looking? Are there other versions of you, right now, living out the consequences of quantum events that branched your history from theirs? Is reality fundamentally dependent on the perspective of whoever is describing it? Is the wave function a description of the world, or of someone's beliefs about the world? Is measurement a physical event, or an act of a conscious agent acquiring information? These questions matter. They matter for the same reason that questions about the nature of time, the nature of causality, and the nature of the self matter, because the answers shape the framework within which we understand everything else. If the universe has no observer-independent state, that is the most important fact about the nature of reality that has ever been established. If the universe branches with every quantum event into equally real parallel versions, the scale of what exists is incomparably larger than anyone assumed. If quantum states are personal beliefs, the relationship between scientific description and objective reality is fundamentally different from what most scientists believe. The physicists who have thought most carefully about these questions have not arrived at a consensus. The debate continues in journal articles, conference proceedings, and informal arguments between careful people who have dedicated careers to thinking about it. The fact that it continues is not a sign of philosophical indulgence. It is a sign of genuine difficulty, of questions that resist resolution because the thing they are questions about is genuinely strange, in ways that our concepts have not yet been fully adapted to accommodate. What is clear, after 100 years of effort, is what the universe is not. It is not locally real. It is not described by a theory with local hidden variables. It is not a collection of independent objects with fixed properties, interacting through local forces, existing in definite states before and independent of measurement. All of that has been ruled out. The Nobel Prize confirmed it. What remains is the positive question, what is it? And that question, asked with full awareness of what the evidence requires, is the most demanding question in science. While physicists were working through the implications of superposition, entanglement, and decoherence, Carlo Rovelli, an Italian physicist who had spent years thinking about quantum gravity and the structure of space and time, proposed something that cut to the heart of the problem from a different angle. His interpretation, which he called relational quantum mechanics, begins with a simple observation: quantum states always seem to be relative to the thing measuring them. Consider velocity. A train traveling at 100 miles per hour is doing so relative to the ground. Relative to another train moving alongside it at the same speed, it is standing still. We do not say velocity is unreal because it is relative. We understand that velocity is a relational property. It exists in the interaction between two objects, not as an intrinsic feature of either one alone. Rovelli's claim: quantum states are exactly like this. The quantum state of an electron relative to Alice, who just measured it, is different from the quantum state of the same electron relative to Bob, who has not interacted with it. Both descriptions are correct. Neither is more fundamental. The electron does not have an absolute, observer-independent quantum state. Its quantum properties, including whether it has a definite value for something like spin, exist only as facts about interactions. When Alice measures the electron and finds it spinning in one direction, a new relational fact is established. Relative to Alice, the electron has that spin. This is real. But relative to Bob, who has had no interaction with the electron, its spin remains in superposition. Both descriptions are valid descriptions of the same physical situation, and they do not contradict each other because they are describing different relationships. In this picture, collapse is not a mysterious physical event. It is the coming into being of a new relation. There is no universal moment at which a superposition becomes definite for everyone. There is only the moment at which it becomes definite relative to some specific other system. The world, in relational quantum mechanics, is a vast network of interactions, a web of relational facts, each real relative to the parties involved, none absolute. There is no view from outside, no God's eye perspective from which the true, complete state of the universe can be read off. Reality is the sum of all its interactions, and that sum can never be taken in from any single vantage point. This is not solipsism. Rovelli is not saying the world is whatever you believe it to be. There are facts in his universe. They are just always relational facts, and the laws of quantum mechanics tell you how the relational facts update when new interactions happen. But it is, undeniably, a universe without an absolute reality. When Rovelli wrote about this in 2025, he said, "We have to live with this lack of total description over reality." He was not being dramatic, he was being precise. The disturbing question that follows is, if no perspective on reality is complete, if every description is relative to some observer, is there anything left of the traditional scientific project? Science has always been about finding the facts that are true independent of who is asking. Relativity kept observer independence for most things. Only velocity and simultaneity became relative, and even those followed universal, computable rules. In relational quantum mechanics, the facts themselves become relative. The electron's spin is not a fact about the universe. It is a fact about the universe relative to Alice. This does not prevent us from doing physics, but it changes what physics is doing. It is not describing an independent external reality. It is describing the web of relational interactions from within it. And things get stranger still with Cubism, an interpretation whose name comes from quantum Bayesianism. Christopher Fuchs, Carlton Caves, and Rudiger Schack developed Cubism over the course of years, starting in the late 1990s. Their starting point, the wave function, is not a feature of the world at all. It is a personal tool that an agent, a physicist, a conscious being capable of taking actions and experiencing consequences, uses to organize their expectations. When a physicist assigns a quantum state to an electron, they are not describing what the electron is. They are describing what they expect to experience if they perform a measurement on it. The Born rule, the formula that converts wave function amplitudes into probabilities, is not a law of nature. It is a normative rule for how rational agents should place their bets. In Cubism, the measurement result is something genuinely new. It is not a pre-existing property revealed. It is not a branch of a universe splitting. It is a novel event created at the meeting point between an agent and the world. The agent acts, the world responds. The response is real and irreducible, but it belongs to the agent's experience, not to some observer-independent fabric. Cubism makes the measurement problem disappear by removing the thing it was a problem for. If there is no objective wave function, there is nothing to collapse. If quantum states are personal beliefs, updating them when you get a result is no more mysterious than updating any belief in light of new information. Critics have an immediate question. If quantum states are personal beliefs, why do different physicists always agree on the statistics? If Alice and Bob both measure electrons from the same source, they get the same distribution of results. Why do their personal beliefs converge? Cubism answers, because they share a world. The world trains beliefs. Different agents, exposed to the same physical processes, rationally arrive at the same probability assignments. The agreement is not evidence of an objective wave function. It is evidence that the world is genuinely there, constraining what rational agents should expect. This is subtle and hard to criticize without careful thought. The world, in Cubism, is real. The agent's experiences are real. What is not real, in Cubism, is an observer-independent quantum state that exists between measurements and applies equally to all observers. Cubism draws on William James and American pragmatism. Truth, in this tradition, is what works. Theories are tools for navigating the world, not mirrors of an objective reality behind experience. Fuchs embraced this explicitly, positioning Cubism as a continuation of pragmatism into physics. Most physicists find this philosophically uncomfortable. Science is supposed to be finding out about the world, not organizing personal expectations. If quantum mechanics is just a tool for betting, what are we doing when we say the universe is quantum? The debate has not been resolved, and it is genuinely hard, but Cubism has one undeniable virtue. It takes seriously the fact that physics is always done by agents with experiences from the inside of the universe they are trying to describe. It refuses to pretend that there is a view from nowhere. The place where the observer problem becomes most viscerally strange is in the Wigner's friend thought experiment. Eugene Wigner proposed it in 1961. The setup. His friend is sealed inside a laboratory. Inside the lab, the friend measures a quantum particle, say, an electron that was in superposition. From the friend's perspective, the measurement collapses the wave function. She has a definite result. She knows the answer. From outside the lab, Wigner knows a measurement was made, but he has not learned the result. He has not interacted with the outcome. According to quantum mechanics, applied honestly, the lab, including his friend and her measuring device and her knowledge of the result, is in a superposition. One branch of the superposition contains the friend having found spin up. Another contains the friend having found spin down. Wigner and his friend are applying quantum mechanics correctly, and they are describing different realities. This is not a paradox about ignorance. Wigner is not simply saying he does not know the result. He is saying that, according to the best physics we have, the result does not have a definite value relative to him until he interacts with the lab. His friend says the result does have a definite value relative to her. Both statements are correct within their respective frames of reference. But what happens if Wigner then opens the lab door and asks his friend what she found? She gives him the answer. Now, did the result become definite when the friend measured or when Wigner learned about it? The friend says her measurement fixed the outcome. Wigner's equations say the outcome became definite for him only when he interacted with the lab. There is no objective moment at which the result became real. Different interpretations resolve this differently. Copenhagen says to apply quantum mechanics from whatever perspective you occupy, without asking about the other perspective. Many Worlds says both outcomes happened in separate branches, and Wigner is about to branch himself. Relational quantum mechanics says both descriptions are correct relative to their respective observers. Cubism says the friend's result is real for the friend, Wigner's uncertainty is real for Wigner, and there is no further fact to look for. What is troubling is that they all require giving up something that seemed unshakable. Either there is one shared reality, or there is not. In every interpretation of quantum mechanics, the answer is not quite. This thought experiment left the laboratory in 2019. A team at Heriot-Watt University in Edinburgh built an experimental version of the Wigner's friend scenario using photons as the quantum systems and beam splitters and detectors as stand-ins for observers. 6 photons, 2 simulated Wigners, 2 simulated friends. In the experiment, the simulated observers obtained results that, when analyzed carefully, were mutually contradictory, consistent with the prediction that quantum mechanics allows different observers to have genuinely different facts about the same quantum event, with no deeper fact that settles which is right. This was not a philosophical puzzle. It was measured data. The experiment confirmed that the logic of Wigner's friend scenario is physically realizable, not just mathematically conceivable. And then it got worse. In 2018, Daniela Frauschiger and Renner published a thought experiment that extended Wigner's friend to multiple observers reasoning about each other. Their theorem proved something stark. If quantum mechanics applies universally, including to agents making measurements, then it leads to logical contradiction unless at least one of 3 assumptions is abandoned. The 3 assumptions: first, that there is only one consistent set of physical facts, that different observers cannot both be right if they contradict each other. Second, that observers can use what other observers concluded from their measurements to make their own predictions. Third, that quantum mechanics applies to all physical systems, including observers themselves. You can keep 2, you cannot keep all 3. Copenhagen gives up the third. Quantum mechanics does not apply to observers in the same way it applies to particles. Many Worlds gives up the first. There is no single fact of the matter. Both outcomes happen. Relational quantum mechanics and cubism give up the first in different ways. Pilot wave theory keeps all 3, but imports radical non-locality to do it. Every interpretation of quantum mechanics requires abandoning something you thought was obviously true. The debate is about which obvious thing to sacrifice. John Wheeler, who mentored Everett and spent decades thinking about the nature of reality in light of quantum mechanics, eventually arrived at a phrase that became famous: it from bit. He meant that the physical world might arise from information, from the yes or no answers to quantum questions. Not matter first, then information derived from matter. Information first, and matter as what information does when it accumulates structure. Wheeler proposed the delayed choice experiment to test a consequence of this idea. In the standard double-slit setup, the particle passes the slits and then hits the screen. If a detector is placed at the slits, the interference pattern disappears. The particle behaved like a particle all along. If there is no detector, interference appears. The particle behaved like a wave. Wheeler asked, what if you decide whether to insert the detector after the particle has already passed the slits? The experimental results. The interference pattern responds to the choice made as the particle traveled, as if the particle traveled as a wave. And then, when you decided to look, it turned out to have gone through just one slit all along. The past behavior of the particle is undetermined until the future choice is made. The particle does not travel through one slit or two, traveling through the apparatus and waiting for a result. Its history is created retroactively by the measurement decision. Wheeler's conclusion: the past has no existence except as it is recorded in the present. This is not a metaphor, it is what the experiment shows. The delayed choice experiment has been confirmed many times. The past is genuinely being shaped by present choices within the rules of quantum mechanics. This does not mean you can change history in the everyday sense. The retroactive effect is limited to the quantum level and cannot be used to send information backward in time. But as a statement about the nature of time and the nature of the past, it is extraordinary. The fixed, settled, already determined past that you intuitively believe in does not exist at the quantum level. The past is a structure that gets built as the present accumulates records of it. All of this, the superposition, the non-locality, the observer dependence, the relational nature of quantum facts, the retroactive shaping of the past, raises a question that physicists usually take care to call speculative. What if the universe itself is a kind of computation? Nick Bostrom's simulation argument, published in 2003, does not require quantum mechanics. It is a probability argument. If advanced civilizations can run simulations of conscious beings, and if they choose to run many such simulations, then the probability that any given conscious being is in a base reality rather than a simulation is low. This argument has been taken seriously by philosophers and scientists. Though it is contested, the quantum mechanics connection is independent, and some argue more compelling. The universe has a minimum length scale, the Planck length, and a minimum time scale. Space and time may not be continuous. They may be discrete, pixelated at the smallest scale. If so, the universe is computable, finite at each moment, changing in discrete steps, describable by a finite set of operations. The universe follows mathematical laws that are, by any measure, extraordinarily compact. Maxwell's equations for electromagnetism, Einstein's equations for gravity, the standard model for particle physics. All of human-scale reality emerges from a small set of rules with elegant symmetry structure. If you were designing a simulation to produce a complex universe efficiently, you might design it this way. Max Tegmark has gone further than almost any other mainstream physicist. His mathematical universe hypothesis proposes that the universe is not just described by mathematics, it is mathematics. Mathematical existence and physical existence are the same thing. Every consistent mathematical structure exists. We happen to inhabit one that supports observers. In Tegmark's picture, the simulation argument becomes almost trivially true. Every mathematical structure that contains self-aware entities contains those entities in the only sense that is ultimately meaningful. There is no extra step of running a simulation. The mathematical structure is the existence. This is deeply strange. It means that everything that could mathematically exist does exist, and the question of why our universe has the particular laws it does dissolves. All possible law sets exist, and we are in the one whose laws permit observers to evolve. This may be too strange to be right, or it may be where quantum mechanics leads when you follow it far enough. What is clear is that the universe, at its most fundamental level, is made of something more like information than like the ordinary matter we think of when we say stuff. Quarks and electrons are not small pieces of a substance. They are patterns of information, states in a quantum system, defined by their interactions with other states. Their properties are not intrinsic. They are relational. Their histories are not fixed. They are constructed as measurements accumulate. This has a disorienting consequence. The further physics goes into the foundations of reality, the more ordinary material objects, tables, rocks, bodies, stars, dissolve into something more abstract and tenuous. Not more ephemeral in a mystical sense, but more strange in a precise, technical, experimentally confirmed sense. The table is real, but what makes it real is a web of quantum interactions, quantum measurements, quantum correlations, and quantum information, none of which behave the way classical objects do, and none of which have settled interpretations in the physics community. There is one interpretation that tries to rescue a fully deterministic, objective reality, the pilot wave theory, proposed by Louis de Broglie in 1927 and redeveloped by David Bohm in 1952. In this picture, particles always have definite positions. There are real hidden variables, not the local ones that Bell's theorem killed, but non-local ones. Each particle is guided by a pilot wave, a wave that fills all of space and responds instantaneously to changes anywhere in the universe. The wave determines the statistical distribution of where particles are found, reproducing all the predictions of quantum mechanics exactly. Bohmian mechanics is deterministic. Every outcome is predetermined by the particle's initial position and the global pilot wave. Randomness is entirely epistemic. We do not know the particle's exact initial position, so we cannot predict the outcome, but the universe knows. Every particle follows a definite path, guided by a wave that knows about the entire universe simultaneously. This sounds almost old-fashioned, a return to classical determinism, just with a strange guiding field. But the guiding field is inherently non-local in a way that cannot be removed. The pilot wave responds instantaneously to every measurement performed anywhere. When you measure one particle of an entangled pair, the pilot wave instantly updates everywhere, changing the guidance for the other particle, instantly, regardless of distance. This is not optional in the theory. It is the mechanism. Bohmian mechanics restores a definite, observer-independent reality. It eliminates the measurement problem. Particles have positions at all times. Measurement simply reveals the position. But it accepts, as a fundamental feature of the universe, a non-local guiding field that violates the spirit of Einstein's relativity, even if it does not violate the letter of it. Every particle in the universe is connected, through the pilot wave, to every other particle. The universe, in Bohmian mechanics, is a single, entangled system with no truly independent parts. Different horror, same address. Objective collapse theories take a different approach. The GRW model, named for Girardi, Rimini, and Weber, modified the Schrödinger equation to include spontaneous, random localization events. Each particle has a tiny probability at each moment of spontaneously collapsing to a definite position. For a single particle, this probability is so small that quantum behavior is preserved across experimental timescales. For a large object with many particles, the collapses happen so frequently that quantum superpositions are destroyed almost instantly. Roger Penrose proposed that gravity triggers collapse. Quantum superpositions involve slight differences in mass distribution, which correspond to slight differences in space-time curvature. Penrose argues that maintaining two different space-time geometries simultaneously is physically unstable. When the gravitational energy difference between the two superposed configurations exceeds a threshold, the superposition collapses. Larger masses, which create larger gravitational differences, collapse faster. Tiny particles maintain quantum behavior longer. Both GRW and Penrose's theory are genuinely falsifiable. They predict specific deviations from standard quantum mechanics at intermediate scales, deviations that have not been observed yet, but that might be accessible with future experiments. If either model is correct, the universe itself provides the collapse mechanism. Measurement is not special. Superpositions just cannot grow too large before reality forces a decision. These are minority views, but they are taken seriously. Penrose is one of the most mathematically sophisticated physicists of the 20th century, and his colleagues treat his proposal as a legitimate scientific hypothesis, not a metaphysical guess. What does all of this mean for you, right now, as a person living in a world that seems solid and definite and observer-independent? It means you are navigating a reality that, at its foundation, does not match the map your brain provides. Your brain evolved to track large objects moving at moderate speeds in a world where quantum effects are completely invisible. It produces the confident sensation that the table is solid, the past is fixed, and objects exist whether or not you look at them. This sensation is a functional model, not an accurate description of what is happening at the level where the laws of physics actually operate. This is not a new problem. Evolution does not select for true beliefs about quantum mechanics. It selects for effective behavior in an environment where classical physics is a sufficient approximation. Your classical intuitions work because decoherence is so fast and thorough that quantum effects never penetrate to the scale where you move and act. You are, effectively, living inside the thick, decoherent crust of a quantum universe. The strangeness is always underneath. You just never touch it directly, except that you do, in a way. The chemical reactions in your cells are quantum. The photosynthesis in plants that produces your food is quantum. The mutations in DNA that drive evolution are quantum events. The universe's quantum character is not sealed away in some separate domain. It is the engine running under everything. The classical reality is the surface, and the surface is not the real thing. The real thing is whatever quantum mechanics is describing, and physicists do not agree on what that is. This is worth sitting with. Physics has been practiced for centuries. It has mapped the solar system, predicted eclipses, discovered the structure of matter, unlocked the nucleus, produced the technologies of modern civilization. It is the most reliable method human beings have ever found for learning true things about the external world. And at the foundation of that method is a theory, quantum mechanics, that every practitioner agrees produces the right answers, combined with a complete lack of consensus about what it means about what exists, what it means about the role of observers, what it means about the nature of reality. The year 2022 brought a Nobel Prize awarded explicitly for proving that the classical, intuitive picture of reality is wrong. That was the result. The Nobel Committee did not add a footnote explaining what the correct picture is, because there is none yet to offer. We are in the unusual position of knowing what reality is not local, not classically real, not fully definite, independent of observation, while being genuinely uncertain what it is. Some physicists find this exhilarating. The question is still open. The hardest problem in science sits unanswered after a century of effort by the best minds the discipline has produced. Others find it disturbing in a way that is hard to articulate. It is not that the answer is unknown. It is that the kind of answer that would satisfy us, a description of the world that is true independent of who is asking, may not be available. Every interpretation either imports radical non-locality or infinite parallel branches, or observer-dependent facts, or modified physics, or some combination. None of them gives back the solid, determinate, observer-independent reality we started with. And yet here you are. The floor is solid under your feet. The room is around you. Your memories feel fixed. The world is apparently going about its business. This stability you experience is real. It is just not what it appears to be. It is the emergent behavior of a quantum system so thoroughly entangled with itself, so thoroughly decohered at every scale of everyday life, that the quantum weirdness underneath is effectively invisible. The table is stable because every molecule in it has been measured by every adjacent molecule, by every photon passing through the room, by the air, by the heat, by the light, many millions of times per second. It has been forced into a definite, consistent, relational reality by the constant measuring activity of the universe around it. But the measuring activity is what makes it real. The table exists as a definite classical object because it is constantly being observed by everything near it, not by a conscious person, but by the physical interactions that constitute, in quantum mechanics, the act of measurement. Remove all that, isolate the atoms of the table perfectly from their environment, and the table would spread into quantum superposition. It would no longer be a definite thing in a definite place. It would become a smeared probability distribution. Physics says this is what the table always is, at its foundation. The classical table you see is a consensus reached by countless quantum interactions, perpetually renewed, perpetually decoherent, never actually resolved. The measurement problem is still open. No one knows what makes the first measurement. No one knows why any definite outcome occurs. The ground is solid under your feet because every atom in it has reached agreement with every other atom about where it is. But we do not know what makes that agreement possible. We do not know what the atoms are before the agreement is reached. And here is perhaps the most disturbing implication of everything physics has found. The question, what is really there? The most basic question you can ask about the universe may not have an answer independent of who is asking it, and when, and in what context. Reality may not be a thing. It may be a process, not a stage set that exists before the play begins, but something that comes into being at the intersection of interaction and information perpetually, at every scale, in every corner of the universe that has ever been touched by measurement. The floor beneath you is solid, the room around you is real, your past is as fixed as the records of it allow. And every one of these facts depends, in ways physics has now made precise, on the ongoing, never completed, perhaps fundamentally incomplete act of a universe measuring itself into existence. We still do not know what makes the first measurement. We still do not know what chooses one outcome from all the possibilities. We still do not know if there is a fact of the matter about what happens when no one is looking, or whether the question is even well formed. The question has been open for 100 years. It will be open for some time yet. And the fact that we can ask it clearly, point precisely to where the uncertainty lives, describe the experiments that have narrowed what the answer cannot be. That is the closest physics has come to explaining how terrifyingly strange it is to exist. The pilot wave theory that Bohm developed in 1952 deserves deeper examination than it usually receives, because it offers the clearest example of what it costs to maintain a fully objective, deterministic quantum mechanics. In Bohmian mechanics, particles are real. They always have definite positions, and those positions are the hidden variables that Bell's theorem seemed to rule out. But Bohmian mechanics is explicitly non-local. The positions of all particles are guided by a pilot wave that exists throughout all of space and responds instantaneously to every change anywhere in the universe. Bell's theorem did not rule out hidden variables in general. It ruled out local hidden variables, variables that could be specified for each particle independently, without instantaneous reference to what other particles are doing elsewhere. Bohmian mechanics evades this restriction by making the hidden variables explicitly non-local. The pilot wave of any system depends on the configuration of every particle in the universe, and it updates instantaneously when any measurement is made anywhere. The non-locality that Bell's theorem proved to be unavoidable is built into Bohmian mechanics as its central feature. This gives Bohmian mechanics an unusual combination of properties. It is completely deterministic. Every particle has a definite position at every moment. The apparent randomness of quantum mechanics is entirely due to our ignorance of the exact initial positions of the particles. If we knew them exactly, we could predict every outcome. Measurement reveals pre-existing positions, not creates them. The wave function never collapses because collapse was never necessary. The particle always had a position. The wave function always guided it, and the measurement simply discovered where it was. But the pilot wave, the guiding wave that determines the particle trajectories, is a global, non-local object. It encodes information about every particle in the universe simultaneously. It updates instantaneously when any measurement is made. When one particle of an entangled pair is measured, the pilot wave responds instantaneously everywhere, changing the guidance for the distant partner particle, producing the correlations that Bell's theorem showed to be real. The advantage of Bohmian mechanics is that it gives a clear, unambiguous picture of what exists and what is happening. Particles are in definite places. The wave function is a real physical field guiding their motion. Measurement reveals where particles are. There is no collapse, no branching, no subjective dependence on observers. Reality is fully objective and fully described by the theory. The disadvantage is the non-locality, which sits uncomfortably with the structure of special relativity. Relativity says no influence propagates faster than light. The Bohmian pilot wave propagates instantaneously. There is no conflict in terms of observable predictions. Bohmian mechanics makes identical predictions to standard quantum mechanics for every experiment, and the instantaneous updating cannot be used to send information. But the physical picture is in deep tension with the relativistic principle that the structure of space and time constrains what can influence what. Extending Bohmian mechanics to relativistic quantum field theory, the framework needed to describe particle physics at high energies has proven technically difficult. Some think the difficulty is temporary, a challenge to be overcome with clever mathematics. Others think it reflects a genuine incompatibility between the Bohmian picture and the structure of relativistic physics, suggesting that if Bohmian mechanics is correct, our understanding of relativity must be revised in some way at the deepest level. What Bohmian mechanics demonstrates most clearly is that there is no free interpretation of quantum mechanics. Every interpretation trades one set of problems for another. Bohmian mechanics gives you objective determinism and definite positions at the cost of radical, global, non-locality. Many worlds gives you universal applicability of the equations at the cost of ontological extravagance, an enormous multiplicity of equally real worlds. Copenhagen gives you pragmatic utility at the cost of refusing to explain the central event in the theory. Relational quantum mechanics and cubism give you resolution of the measurement problem at the cost of observer-relative or agent-relative reality. The choice between interpretations is not a choice between a right answer and offer wrong ones. It is a choice about which features of the world to prioritize and which uncomfortable implications to accept. And since no experiment can currently distinguish between the interpretations, the choice reflects philosophical values as much as physical intuition. There is, however, one class of interpretations that could in principle be distinguished from the others experimentally. These are the objective collapse theories, which modify the Schrödinger equation to include a real, physical collapse mechanism. The most developed examples are the GRW model, named for Girardi, Rimini, and Weber, and Roger Penrose's gravitational collapse proposal. The GRW model adds a new term to the Schrödinger equation. Each particle has a small but finite probability per unit time of undergoing a spontaneous localization, a random collapse to a definite position, after which it spreads back into superposition. The collapse rate is set so that for individual particles, collapses are extremely rare enough that quantum interference experiments are unaffected. But for a large object with many particles, the combined probability of at least one particle collapsing in any given short interval is very high. The object's quantum state is constantly being localized by the spontaneous collapses of its constituent particles, and the result is that large objects maintain effectively definite positions, while small numbers of particles maintain quantum coherence indefinitely. The GRW model makes specific predictions that differ from standard quantum mechanics. The spontaneous localization introduces a small amount of heating into any system, energy added by the collapses. The rate of decoherence predicted by GRW differs slightly from the rate predicted by ordinary decoherence. These differences are small, but they are in principle measurable. Experiments designed to test GRW are actively being pursued, and the results so far have not shown the signature effects the model predicts. But the experiments are also not precise enough to definitively rule it out. Roger Penrose's proposal is more speculative but more physically motivated. Penrose argues that gravity, the force described by Einstein's general relativity, plays a role in wave function collapse that standard quantum mechanics ignores. In quantum mechanics, a particle in superposition occupies multiple positions simultaneously. Each position corresponds to a different mass distribution. Each mass distribution corresponds, through Einstein's equations, to a different geometry of spacetime, a different curvature of space and time. The superposition is thus a superposition of different spacetime geometries. Penrose argues that maintaining two different spacetime geometries simultaneously is physically unstable. Spacetime, he suggests, cannot tolerate superpositions of its own geometry indefinitely. When the gravitational energy associated with the difference between the two superposed geometries exceeds a threshold, the superposition collapses to one of the two. The timescale for this collapse depends on the mass involved. Massive objects create large gravitational differences and collapse quickly, which is why large objects appear classical. Very light particles create negligible gravitational differences and can maintain superpositions for long periods, which is why quantum behavior is readily observable in electrons and photons, but not in cats. This proposal has attracted both enthusiasm and skepticism. It is genuinely novel. It is the only major proposal that suggests a direct connection between quantum mechanics and general relativity at the level of the measurement problem. If Penrose is right, quantum gravity is not just a technical problem to be solved by combining the equations of quantum field theory with general relativity. It is physically relevant to the most basic act of quantum mechanics, the act of measurement. The two great theories of 20th century physics are not just formally incompatible at extremely small scales, they are in tension at the human scale. Every time a quantum event occurs, the experimental tests of Penrose's proposal are in progress. The predicted collapse times for various mass configurations have been calculated. Laboratory experiments using optomechanical systems, tiny mirrors, cooled to near absolute zero and placed in quantum superpositions, are approaching the sensitivity needed to detect or rule out Penrose-style collapse. The next decade of experiments may provide genuine evidence bearing on whether gravity plays a role in the resolution of quantum superpositions. What is the right interpretation of quantum mechanics? After a century of effort, the honest answer is nobody knows. The experimental evidence confirms that quantum mechanics is the right theory. The mathematical formalism is clear and precise and works perfectly. What the formalism means, what it is describing, remains genuinely contested. A survey of participants at a Quantum Foundations conference in 2011 found that roughly 40% preferred the Copenhagen interpretation, 18% preferred many worlds, and the rest were distributed across various other options or chose none. More recent surveys show a trend toward many worlds gaining ground among younger physicists who find it the most mathematically honest. But no interpretation has achieved consensus. The persistence of the debate is not a sign of philosophical indulgence or professional failure. It is a sign that the question is genuinely hard. Quantum mechanics describes a universe whose behavior at the fundamental level violates every intuition developed by creatures living at the classical scale. Our concepts of reality, of properties, of causality, of the past and future, of the boundary between observer and observed, all of them were developed in a world where quantum effects are invisible. None of them cleanly translate to the quantum domain. The progress that has been made, and it is genuine, substantial progress, is in sharpening the question. We know now, with precision, what any acceptable interpretation must accommodate. It must accommodate the violation of Bell's inequality. It must accommodate decoherence and the emergence of classical behavior at large scales. It must accommodate the Wigner's friend scenarios and the Frauschiger-Renner theorem. It must accommodate the exact predictions of quantum field theory, which is the most precise theory ever constructed. And it must make sense as a complete account of what the universe is doing, not just as a calculation tool. No interpretation yet fully succeeds. Some come closer than others in different respects. The debate continues. And this continuing debate sits at the foundation of everything. Every time you turn on a light, the photons emitted by the filament or the LED obey quantum mechanics. Every time your body metabolizes energy, the chemical reactions proceed through quantum mechanical transitions. Every time the sun fuses hydrogen into helium, the process involves quantum tunneling through an energy barrier that classical physics would not permit. The universe runs on quantum mechanics, and no one fully understands what that means.